Welcome to everybody. Let's give 5 minutes for the rest of the people to join in, and we will begin. Well, welcome to everybody. This is Solar USA's first webinar, first training. We're going to be having more and more collaborations with different brands. So hope you can be, looking at your emails so you can, um, see all of our new trainings. My name is Alejandro Canto, by the way, Tech Support Coordinator for Solar USA. All right, so ready? Thanks for everybody to joining in, and we'll be beginning in a few minutes. Okay, so let's begin. As I said already, this is our first webinar, our first training, so we're going to be going with the basics. My name is Alejandro Canto, Tech Support Coordinator. For those who don't know me, I look for all the warranties and all the tech situations for Solar USA. So, just as an introduction, I want you guys to know that in this presentation, solar energy with photovoltaic technology, we're going to be speaking about facts and about a bunch of subjects that are just related to the premise of solar energy. This is just our first training, so we're going to be going with the basics. Let's begin. The subject today is going to be solar energy with photovoltaic technology. Okay, so let's begin with this phrase. It was said by Nikola Tesla. Through space there is energy, and it is a mere question of time when men will succeed in attaching their machinery to the very will work of nature. We have to understand that whenever I said will work of nature, I'm referring to the solar energy and the sun. This because this is just a natural resource that we have day by day, and if we learn to harness it, we'll be getting with a better society and better technology. And we'll go further in just technology advance. So first, talking about the subjects that we're going to be talking about in this first webinar is going to be the origin of solar energy, photovoltaics, the manufacturing process, how is it made, how are we making the solar cell from the beginning, from the start, and physical fundamentals. How does the solar cell works and how does a solar model works in the very basics with the physics and the chemistry in it. Also, we're going to be speaking about the elements of a photovoltaic model, the layers, and how is it composed. So let's begin. So with our first subject, origin of solar energy. First, we have to understand what is energy, because there are a bunch of phrases that include the word energy. We can speak about kinetic energy, gravitational energy, or even the word energy drinks. But we have to understand that energy is not always the same. So in the basics, energy is the capacity that bodies have to produce a work. For example, a mechanical work, emission of light, generation of heat, and with generation of heat, we can even make electricity. So yeah, energy is just a compound word of, well, a very complicated structure. So energy can manifest itself in different forms. As I already mentioned, gravitational energy, that is the energy that is pushing us all together in the same world. Kinetic energy, chemical energy, electrical energy, that is the one that's going to be more related to us because we want to talk about photovoltaic energy, that is also traduced as electric energy, nuclear energy, and there's a bunch. So with the possibility of transforming from one to another to get the best out of it. So first, we have to understand what's the origin of solar energy. The sun, of course, is the one that's going to be our premise. The sun directly or indirectly is the source of all or most of renewable energy, except with tidal and geothermal energy. But even wind energy comes from the sun because the rays of the sun are the ones that are going to be making that the wind happens. So if we want to harness just the subject of solar energy, we're going to speaking about the different radiations that we can get. We can get diffuse radiation, direct radiation, or reflected or albedo radiation. As we can see in the image of the right, we can see the explanation of how there's a different meaning for the same radiation. We can speak about direct radiation, that is going to be the radiation that comes directly from the sun to us or to the solar model, is we're going to be speaking just about solar energy. Or we can talk about diffuse radiation. Diffuse radiation is whenever the sunlight or the sun beam hits a cloud and it just diffuses and it gets back to the solar model. Also, we can talk about reflected radiation. Reflected radiation is the one that's going to be, as the word itself says it, reflected by any flat surface. It can be reflected by grass, it can be reflected by snow, or even by a roof. This is very interesting because as solar model manufacturers, we harness or we try to harness the most radiation that we can. I'm sorry, I was letting the rest of the people join in to the webinar. Also, by the way, for the Q&As, any questions that you have, we're going to be leaving a space at the end of the presentation so you can fill up any questions that you need. You can just put your hand up in the Zoom and we'll accept you. Okay, so as I was saying, the origin of solar energy, of course, is going to be coming by the sun, and the radiation is never going to be the same. We have different types of radiation: the direct, the diffuse, and the reflected radiation. So, as we know, the sun ray can transform in different ways. It's not just for making electricity, but it can also give us heat. So, in this presentation, we're going to be speaking about the different sources of electricity. So solar energy has been utilized directly or indirectly for centuries in various activities. The sun can be harnessed for energy purpose in two different ways. In the image of the left, we have a solar heater, and in the image of the right, we have a solar module. As a source of heat, we can be using solar thermal energy at low or medium temperatures, and this equipment is called a solar heater. And in the right, we have a solar module, the one that we manufacture, and we can use it as a source of electricity. Photovoltaic solar energy and high temperature solar thermal energy can give us electricity. So yeah, we can get electricity with a solar heater. It's just with a very, very much higher temperature. So as we can see in this diagram, solar energy can be divided in two different ways. So it can go with a photothermal process and a photovoltaic process. Whenever I say photovoltaic process is whenever we're speaking about the solar cell and about the solar model, and we're just going to be basically making electric energy. But if we go to the other side, to the photothermal processes, we're going to be working with heat, with temperature, and we can divide it in two: low temperatures and high temperatures. As we know, low temperatures are just going to be for water heating, so we can just use it to take a bath, for example. And whenever we are working with high temperatures, then the game is going to be changing. It's going to be a lot different. We're going to be using equipment as a heat exchanger or a heat turbine, and this is going to help us to generate more electricity. This with an electric generator, and this electric generator is going to give us electricity. So yeah, we can get electricity with both sides, with the thermal energy of the sun and with the photovoltaic process of the sun. Okay, so now let's talk about the manufacturing process. How is it made? Because as we know, solar cells go through a very hard process to be done, and they're very, very thin. So first, let's talk about the prime material, silicon. So what is silicon? Going on with the basics, it's just a material. Silicon is a crystalline element that doesn't exist in its free form, but rather in the form of compounds. Compounds that we know and that we see day by day, such as sand or quartz. Quartz and sand both can be get in mines, and there are such things as silicon mines that are just mines that do the job to get the best silicon of the place. In recent decades, new applications have emerged in the field of electronics because, as we know, silicon is a good transmitter of electricity. So we can use it in microelectronics or in the production of a photovoltaic solar panel, as we're going to be harnessing in this part of the presentation. So, as we can see in the image of the back of this phrase, this is a silicon mine, and pure silicon is extracted from the sea, sand, or quartz through the furnace. This process yields silicon with a purity ranging from 98 to 99.5 of purity, but this is not going to be enough because we need 9N silicium. What do I mean when I say 9N silicium? I say, when I'm trying to speak about a silicium that has a purity with a 9N or a 9 digit 9, okay? So it's going to be 99.99999% of purity. I know it's a very confused process, but yeah, we're just trying to get a thing that we call primary silicium. Primary silicium is the best silicium because it's going to be the one that is going to help us conduct more energy whenever we're producing a solar panel. As it says in the presentation, it's an ultra pure silicium, or we can also call it electronic grade silicon. These are all different names for the same thing: the best silicon or the most pure silicon, 9N silicon. So when we speak about the wafer production, we're speaking about the same silicon, the electronic grade silicon, but cut it into wafers. Whenever we're cutting this silicon, this electronic grade silicon, we're going to be losing 50% of the material. Why? Because it's so pure that whenever we're breaking and making the wafers, there's a bunch of silicon that is going to be lost, and it's just going to become dust. So we're going to be with the result of a wafers about 200 to 400 micrometers thick. Instead of micrometers, we can just say 0.2 millimeters thick. I'm just trying to say this for us to understand how thin the solar cell is going to be. This thin, you can just break it with your both hands, And to make these wafers, we're going to be using sols with stainless steel cores and diamond edge liquid matrix or liquid. This is just for us to get the most pure wafer and the most thin wafer. Okay, so now whenever we're going to be speaking about the manufacturing process of the photovoltaic model, we can see this image that is just a line of production from the beginning being in the mines, whenever you're getting just the silicium, not electronic grade silicium yet, just silicium, to the solar model. We can divide this line of production in four because, of course, every part is going to be harnessing a different activity. So let's begin with the first two sides. We're going to be speaking about the production of solar quality silicium and then the production of the wafer. These are different processes because we're going to be using different equipment and trying to harness different objectives. In the first, we're just trying to get the silicium that we're going to get from the mine to be a solar quality silicium. In the first step, called manufacturing of metallurgical grade silicium, we're going to take the silicium to a big oven and put it in very, very high temperatures. This process is called the Swarovski method. And this is just basically putting the silicium in a very, very hot oven so we can get the most pure out of it. But this is not just the whole process because then we have to obtain and purify the metallurgical grade silicium that is going to be the silicium that we're going to be working with. In this process, we're going to be putting the metallurgical grade silicium in another oven, and we're going to take it again to very, very high temperatures so we can get the silicium, instead of being dust, we're going to be getting it in chunks. It's very important for us to understand why do we want the silicium in chunks. We want the silicium in chunks because then we're going to be producing ingots. And these ingots here are the ones that we're going to be cutting to make the wafers that I already mentioned in the past presentation, in the past slide. And well, whenever we're getting the ingots, we're getting this very, very big piece of silicium, and then we have to polish it and cut the ingots. Whenever I say polish it, we're going to be polishing with chloride acid. This is just to clean all of the impurities, and with the chloride acid and the diamond blade, we're going to be getting the most thin silicium and the best quality electronic grade silicium. And in the last part of the getting the wafers part, we're going to be getting the lasers and just getting the wafers. But there's a big difference between wafers and photovoltaic cells, because the wafer is just a very thin piece of silicium, and a photovoltaic cell has already the electronic cables and stuff. So let's go with the third part of the process, or the third part of the line of production, that is the production of photovoltaic cells. Because we already have the wafer, but we don't have the photovoltaic cell yet. So the sixth part is the texturization of the wafer. How are we going to be texturizing the wafer? We're going to be placing these chemical solutions in the wafer so we can get the most purity out of it. In the seventh part, we're going to be doping the wafers. How are we doping the wafers? We're going to be placing chemical elements in the wafers. There are two different types, N types and P types. We're going to be talking about this subject further in this webinar, but it's very important for us to understand that there are two different doping methods. We can dope it with P method or with N method. Different chemicals, but with the same objective, just to make the electric current faster. Then we're going to be applicating the anti-reflective layer. This is just for us to be getting the best absorption of the sun. This process is also going to be doing with physical-chemical processes. And in the 10th part, we're going to be connecting the cells. How are we connecting the cells? Placing the ribbons in the wafer. In this part is whenever we are starting to produce the photovoltaic cell, and it's going to be stop being just a wafer. We're going to be having texturization. We're going to be having electric wiring, and this is the way this is going to work. In the part of the metallization is whenever we're putting the very, very small electric circuit in each cell. So the current made by the photovoltaic process can go through the whole cell and through the whole model, so we can be getting the electric energy. And then in the 10th part, we're going to be connecting the cells with the ribbons. So as you guys know, solar cells are connected in series. So if I have a cell, I have to connect the other one right next to it, because in this part, we're already making the solar model, the solar panel. So the first part of making the solar panel, of course, is going to be connecting the cells through the ribbons. And the 11th part is encapsulation of the cell. How are we encapsulating the cell? We have different layers on the solar model. We have we have the frame, we have the tempered glass, we have the EVA, and we also have the TPT. So we have to encapsulate all the layers so we can get the whole solar model, of course. How are we encapsulating it? With a heat press and with a chemical process, so the model is not gonna be shaking, and we're gonna be getting, well, the whole solar panel. In the 12th part, we're going to be finishing the work and assembling the model. As you know, first we're going to be encapsulating the cell in each layer, and then we have to put the frame. So the model is basically all just done. In the 13th part, we're going to be doing the verification and testing. How we're going to be doing this? In Solar Reverse Fabric, we have a solar simulator. This is a very big equipment. Whenever you put the solar model and we simulate the sun to see that it's going to be working, and to see that it's going to be giving all of the electric parameters that our data sheet tells us. And the 14th and the last part is just the photovoltaic model. Is whenever the job is done, and we get, well, the best out of it. Okay, so now let's speak about the physical fundamentals. How does a solar panel or a solar cell works, and what is the physics and the chemistry, behind the whole process? So, of course, the first thing that we need to know and to understand is the photovoltaic effect. How does it works, and how is there a negative and electric and positive electrode in just one cell? So, the photovoltaic effect harnesses solar radiation to excite the free electrons in the semiconductor material. What is the semiconductor material? The already mentioned silicon. Therefore, a photovoltaic model requires direct radiation to react to its nominal operating values. When I say direct radiation, just as in the image that I showed in the beginning of the presentation, direct radiation is the sunbeam rays that hits directly to the model. So therefore, a photovoltaic model requires this direct radiation to reach its nominal operating powers, or the potency that we're harnessing. But it still functions whenever it's exposed to diffuse radiation, or not just direct radiation. It can also work without better radiation or with a diffuse one. So as we can see in the image, the sunlight is going to be hitting the solar cell, and with the negative and the positive electrons, the electric current is going to be able to flow and get out of the solar model to get the electricity that we want for our houses or our businesses. Speaking about the physical fundamentals, we have to understand what's the length of the solar rays that we're going to be harnessing, or that we need to make this electricity. The minimum energy required to break a bond and generate an electron-hole pair is a constant quantity, characteristic of the semiconductor material, known as bond energy. We need to reach this bond energy to generate electricity. And in the case of silicon, the energy required to generate an electron-hole pair is 1.2 eV. When I say eV, I mean electron volts, and this measurement is just made for understanding the electronic spectrum. I'm showing you this image on the low because the visible light is going to be around 1.6 and 3.1 electron volts. But whenever we're trying to make electricity with silicium, we're going to be trying to get 1.2 electron volts. And whenever I said at the beginning or at the middle of the presentation, when I was speaking about the doping of the materials, well, there are two different types of doping methods, the P and the N. We have to use both to generate electricity in a solar cell. So whenever we have our solar cell, we have to dope it with N-type and P-type semiconductors. So when we speak about the N-type semiconductors, we're going to be introducing pentavalent impurities to the solar cell. There are different elements that can do the job, such as phosphorus, that is the most common, phosphorus, antimony, and arsenic. As I said, phosphorus is the most common one, and phosphorus is the one that is going to be having an extra electron. This extra electron is going to be working because if we have an extra electron and the P-type semiconductor has a hole, then this electron is going to be able to move. So we're going to be adding the N-type semiconductor to one of our solar cells so we can have an extra electron. As I said, if we have an extra electron and the P-type semiconductor has a hole or is lacking of one electron, then the electron that is going to be exceeding can be able to move from the N-type to the P-type. And this movement of electron is going to be the thing that is going to give us the electric current and the electricity that we're going to be trying to get. So when I say the P-type semiconductors, I'm talking about different chemicals such as boron, indium, and gallium. Boron, the first one that I mentioned, is the one that is mostly used for solar models. And into the intrinsic semiconductor, a P-type semiconductor is formed. So imagine, just look at the image of the presentation. The P, the red circle, has an extra hole in the down right corner, and this hole is going to be moving to the P-type, to the N-type hole. Why? Because okay, so yeah, as I was saying, since the N-type has an extra electron and the P-type has a hole, this movement of electrons is going to be getting us the electric current. And this is where we get the p-n junction. As I said already, one is going to be having a hole and the other one is going to be having an extra electron. So this is going to be making the electric flow, the electric current. So this junction is crucial component in various semiconductor devices, such as such as a solar model, such as diodes and transistors. Diodes are the ones that we're going to be using because, as we know, diodes are present in solar models in the junction box, and this diode is going to help us to move the electricity from one solar model to another and then to our inverter. So it forms a barrier that allows for the control of the flow of the charge carriers, electrons, and holes, and it's fundamental to the operation of these devices. As we can see in the image, there is the N-type and the P-type, different type of solar cells, and one is going to help us move the electricity from one to another part. So silicon crystals are doped with N-type and P-type impurities just for the objective of helping us to move the electric current in a faster way. And now let's talk about the components of a photovoltaic model. As we know, a photovoltaic model has different layers. It's just not just the silicium or the solar cell. Of course, the solar cell is the most important part of the whole model, but we need to understand the rest of the parts just so we can act properly in the installation and in the handling of the models. So for a model to operate at its maximum efficiency, its components must have characteristics that minimize the performance losses. Why am I saying this? Because the best quality of the products that we have is going to help us harness the best electricity or the best electric generation for the model. Of course, if we have the best tempered glass and the best frame, we're going to be having less losses and a better electricity generation in the whole process. So as we can see in the image, we have different layers, such as the glass, the encapsulant, the solar cell, the ribbons that are inside of the solar cell, the encapsulant, and the junction box. When we speak about the front cover, it's typically made of tempered glass, white tempered glass, because tempered glass is very good for electric conductivity. So it's usually a range of width of from 3 to 4 millimeters. It is not that much of a big of a width. And it has excellent solar radiation transmission, as I already said. We use tempered glass so we can get the best electric current to the cell. Because if we have a very, very thick tempered glass, then no radiation is going to be hitting the solar cell. And if no radiation is hitting the solar cell, then we're not producing any energy. And it also provides protection against weather condition and impacts. As we know, weather conditions such as shadow or rain can affect the performance of the solar model. So we want to give the best performance out of it. So of course, we want to get the best front cover that we can get. Now, a very important part and a very important layer of the solar model is the encapsulant. In most models is called EVA. EVA means ethylene vinyl acetate, and it's just basically a very, very thin plastic that is going to be help us to attach all of the layers of the solar model. It comes into direct contact with the solar cell, so it's going to be the cell, then the EVA, and then the glass. And the EVA is going to be protecting the solar model from shattering with the glass, and it's going to be also help to protect the connections between them and providing resistance to the whole cell. In the part of the back of the solar model, there's going to be another encapsulant because, as I said, the encapsulant is going to be the thing that is going to be protecting the cell. So we're going to be needing the EVA in the top and in the bottom of the solar cell. And after, we're going to be using the back cover, a layer of polyvinyl fluoride that we can call PVF, commercially known as Tedlar, or polyester, together with the front cover, and it protects the model from moisture and other atmospheric agents while providing electrical insulation. Why do we want electrical insulation and protection from moisture? Because we know moisture can give us a lot of problems with the performance of the model, such as hotspots or snail trails. And we don't want it to happen, so that's why we need to get the best layering out of it. And just to finish, we're going to be speaking about the frame. Most of the frames are just made of anodized aluminum, and this just is done for the temperature relationship. Of course, we don't want the model to get very, very hot because we're going to be losing current. So anodized aluminum is very good with managing temperature. Okay, so I know this was very basic and very, very quick, but thank you for your attention and hope to see you in the next webinar. If you have any questions, you can just raise your hand and I'll be very happy to assist. No. All right, so don't worry about it. If there are no questions, hope to see you in the next webinar. We're going to be going further with the subjects. We're going to be going with harder subjects so we can learn how does the solar model works and how can we harness the best sun energy out of it. Thank you and see you in the next webinar.